this section, we'll be going over the constant rule in calculus, which falls under differentiation. Let me go up to the top. So as you can see here, we're working right down the list. In the previous sections, we talked about finding the derivative using the limit process, and then we found the slope of the tangent line, and then we wrote the equation of that line, of the tangent line. And if you remember back up here, find the derivative by the limit process, this kind of got hairy. If these polynomials that we were working on, they become x squared or x cubed or x to the fourth. Now, we just focused on the polynomial functions. I think I did do a rational function where we found its derivative, but we're just trying to keep it simple. So there's all kinds of different types of functions out there, but we're just doing the bare bones here so you can get the basic understanding of how to get started in calculus, or maybe you're just going through and refreshing your memory. So now we're going to get into the actual rules of differentiation, and they're actually pretty simple. There's like 5 or 6 of them that we're going to be going over. And of course, the first one's the constant rule, and this is definitely the short way of finding the derivative of a function than trying to use compared to trying to use the limit definition. All right, so the first one's the constant rule. So let's go down here and take a look at that. So let's say that our function is, we'll call it, well, I need to bring this up first, I guess. Do some little modifications here. We'll say f of x is equal to 3. Okay, f of x is equal to 3. Now, 3 is just a constant. If we were to actually look at the graph of this, you could see here that if we graphed f of x is equal to 3 and look at what we get is just a horizontal line that passes through the y-axis here at 3. And if you picked any point on this line, of course the slope is going to be 0. Right? Think about the tangent line. A tangent line at this point right here, the tangent line is just a horizontal line that you're going to get a slope of 0. So when we go to take the derivative of this, the derivative should be 0. Okay, so this was the very first problem that we worked when we were finding the derivative using the limit process. However, what we're going to do here is we're going to state a theorem. We're not going to prove any of these theorems. We're just going to state them. And I'm going to go ahead and just write it out, that the derivative the derivative of a constant function, which is the one we have here, is 0. Well, is 0. Okay, and let's move this down to the next line. And that is to say that, let me just write it more generally here. If I said f of x is equal to c, where c is any real number, c is any real number then what we can say is, now this is going to be some different notation here that we haven't talked about, but I need to go ahead and this is a good time to actually use this notation. What this is, now we actually did see this when I brought up some graphs in some previous problems. This d over dx, and what this is it's an operator, and what it's saying is, okay, we're going to operate on this whatever's inside this bracket here. In other words, this operator is we're going to take the derivative of whatever's inside, and of course it's just a constant. So this c is just some real number. For example, 1, 2, 3, 4, 5, 6, 7, 8, 9, a half, -5, negative a half, negative square root of 2. Okay, so whatever's on the real number line, pick a point. And when we take the derivative of this, we're going to get 0. Now you can simply prove this. You can simply prove this by using that, remember the limit definition that we talked about in the very beginning. Right, and I'll just go ahead and state it here, and I'll just bring it up, maybe let you do the proving on it. I said we weren't going to do any proving, but all right, so this was f of x plus, remember, delta x. This is actually an easy one to prove. They won't be so easy once these functions get a little bit more difficult. Take my word for it. And that's all over delta x. So you've seen this before. You've seen it before. And in this particular case here, our function happens to be, right, this is our f of x right here, and if we plugged in x plus delta x into this, of course we don't have a variable over here. So f of x plus delta x is just going to equal c. See, so this whole thing right here will just equal c minus, of course, it'd be minus c, because f of x is equal to c, and c minus c just becomes 0. And when we go to simplify this thing down, c minus c is 0. You get 0 over delta x, and 0 over delta x is just 0. And when you take the limit of delta x as delta x approaches 0 of 0, you just get 0. See? Okay. So that's the reason that the derivative of a constant is going to always be equal to 0. Always equal to 0. Now, in this section here, since we went ahead and talked about some different notation, we might as well talk about some more different types of notation. And that is, if we were asked to find y prime, well, y prime, and here's an example, let's say y is equal to some constant, and we want to find y prime. Well, y prime is the same thing as saying we need to find the derivative. Okay, we need to find the derivative. So let me just go back. Let me go up here. So first it was f prime of x. We wanted to find, that's the derivative. Okay. Y prime is the same thing, find the derivative, which in this case is 0, because remember the derivative of a constant is 0. Or we might have a situation like this up here, where you have d over dx. Okay, so these are the three types of notations, and I'll be mixing them up as we go, okay, when we're asked to find the derivative. All right. Okay, so that's going over the constant rule, pretty simple, and we'll be moving on to the next rule.